Hello, everyone. Today we have the Postdoc seminar series. We will start with Dr. Muhammad Lamsan in the topic The Potential of Machine Learning to Enhance the Computational Field Dynamics.
Thank you very much. I am Muhammad Ramzan, and today
ผมต่อเลยปะใครปิดไฟอ่ะ
the title of my presentation is the potential of machine learning to enhance the computational fluid dynamics. So first of all, I will discuss some basic definitions related to the fluid dynamics. A fluid is a substance that may continuously deform under the appliance of an external force or shear stresses. The example of the fluid are water, oil, gases, and blood. Mostly in our study, we use two different types of fluid, Newtonian and non-Newtonian fluid. Newtonian fluid behave according to the Newton law of viscosity, which states that the rate of deformation of a fluid is directly proportional to the applied shear stress, while the second one is the most important, non-Newtonian fluid. The non-Newtonian fluid do not follow the Newton law of viscosity. Types of fluid flows. Here are three different types of fluid flow: one-dimensional, two-dimensional, and three-dimensional flows. In one-dimensional flow, mostly the velocity of the fluid being only in one coordinate system. And two-dimensional flow is defined as the flow type where the velocity of the fluid is the function of two spatial coordinate x and y. But in three-dimensional flow, the velocity of the fluid being is influenced by three spatial coordinate system x, y, and z. But in our work, we mostly study two-dimensional and three-dimensional flow problem. So the main objective, this research aimed to develop and evaluate an ANN-based predictive model for nanofluid flow due to the stretching surface, to extract the data for velocity, thermal energy prediction, and concentration profile, and use them to train ANN model. So in the methodology of the present problem is based on the Navier-Stokes equation, and also for the simulation of the present problem, homotopy analysis method and homotopy perturbation method are involved for solving the nonlinear differential equations. And also we have used this method for the extraction of the data, that after the extraction of the data, we will try to implement the machine learning technique. So mathematical modeling and geometry. This study focuses on the modeling nanofluid flows with application in energy systems. In the present problem, the flow is two-dimensional and the flow is non-Newtonian fluid, the Kazan fluid model. And different fluid flow assumptions are taken as such as magnetic field implementation, thermophrasis, and Brownian motion diffusivity. Here, thermophrasis and Brownian motion diffusivity is used to find out the heat and mass transfer in the present flow problem. So, in the stretching sheet, in the figure, the fluid motion is produced due to the stretching of the sheet. Here, on the surface of the fluid, these are the boundary condition are defined: u is equal to ax power n, y0, t is equal to t infinity, and dB is the Brownian diffusivity, and partial c by partial y, partial d or partial t by partial y, with dt as the thermophrasis diffusivity. The fluid is taken as a Kazan nanofluid, and the nanomaterial size nanoparticle are defined on the geometry of the problem. Before we have modeled the problem, I have defined here some generalized form of basic governing equations. First one is the continuity equation. which express the conservation of mass for an incompressible fluid. And second one is the momentum equation, which is also known as the Navier-Stokes equation. And the last one is the energy equation. On the base of these equations, we formulate our problem according to the present geometry. The geometry is, as I have mentioned, the geometry is stretching sheet. So according to the present flow problem, the continuity equation is defined partial W1 or partial X, partial W2 or partial Y. This is the continuity equation for the present problem. And the momentum equation for is defined as, second one is the momentum equation and third one is the energy equation. So, and the last one is the concentration equation in term of C. C is the concentration of the fluid. So, in term of all these equations, we have defined the boundary conditions according to the present problem. So, after the boundary conditions, we have defined some similarity variables W1, W2, theta and eta and phi. By using these similarity variables, we will convert all the above equations into a non-dimensionless form. Here is the non-dimensionless form of velocity equation, temperature equation, and concentration equations. Why we convert all these equations into the dimensionless form? Because we want to apply the numerical technique. So only we have used the numerical technique on the ordinary differential equation. So that's why we will convert all these partial differential equation into ordinary differential equations. So along with their dimensionless boundary conditions are defined f prime 0, f0 is equal to 0, and theta 0. These are all the dimensionless boundary conditions. During all this simulation, when we convert partial differential equation into the ordinary differential equation and into a dimensionless form, we got some dimensionless variables. Here I have defined some dimensionless variables. Here M is the magnetic field, PR is the Prandtl number, S is the segment number, and NB and NT are the Brownian motion and thermophoresis parameter respectively. So here is the equation that we have to use to find out the skin friction coefficient and the heat transfer rate. Here theta prime is the heat transfer rate. Mostly we used a numerical technique on these equations, and we will apply find the graphical solution against velocity, temperature, and concentration of the fluid, and also we will extract the data to extract the data in the tabular form, and we will try to apply the machine learning technique. So here is the some graphical results. In these figures, the velocity of the fluid decreases due to the increase of the magnetic field. It is only due to the fact that when we increase the magnetic field, the lower force in the fluid motion is produced, which slow down the motion of the fluid particle. As a result, the fluid speed become lower. As a result, the velocity of the fluid decreases. So in the case of the Kazan fluid parameter beta, the velocity of the fluid is also decreases because when we increase the Kazan fluid parameter beta, the velocity, the viscous forces in the fluid become higher. That's why the velocity of the fluid decreases due to the Kazan fluid parameter. Similarly, Prandtl number, with the increase of the Prandtl number, the temperature of the fluid decreases, and also the temperature of the fluid increases in the case of thermophoresis effect. These two figures shows the behavior of segment number and thermophoresis parameter on the concentration of the fluid. The fluid concentration become lower in the case of the segment number, but the fluid concentration become higher due to the increase of the thermophoresis parameter. These results we have to find by using a numerical technique, as I have mentioned in the earlier slide. So this is the table for the heat transfer rate. In this case, in this table, the NUX represent the heat transfer rate. We have shown different effects of different flow parameters on the heat transfer rate, and we observe that the heat transfer rate decreases in the case of index parameter n. So in the case of m, heat transfer rate also decreases, as I have mentioned in the last tabular data M, and with the increase of them, the heat transfer rate is decreases. So now, when we apply the numerical technique and find out the data in the tabular form, and we will try to apply the ANN framework and in the form of machine learning. So here is three different layers, as we know that input layer, hidden layer, and output layer. The main function of the input layer is it takes the data and convert the data into the hidden layer. In the hidden layer, which consists of a different neurons and activation function, which make the computations and convert the data into the output layer. In the form of the output layer, we have trained the data in the form of velocity, temperature, and concentration of the fluid to find out different results like a loss function, mean square error, and root mean square error. This is find the performance evaluation of the model, how our model is exactly accurate. So here I have mentioned some of the results that we have found by using a machine, by using the mean square error, where red line shows the test, validation, and train, and the best approximation is shows at the 1000 epochs, where it shows at the rate of 10 raised to power minus 5, it shows the best performance evaluations. Similarly, in the gradient function, which shows in the second figure, it shows the gradient function mu and the validation of the results. And error histogram, in the error histogram, which different lines shows the trainings, validation, test, and zero error. If we say see at the center point, it almost approximately approaches to the negative, approaches to the zero. So it means that our approximatory error are approaches to zeros, which shows the validation of the present results. So in the next figure, we have to show the function fit for the element 1. In this output and target value, the error almost approaches to the 1, so which shows the validation of our work. So here we have find different trainings, validations, and targets of the results by showing that here R1 and R in the case of training and validation, which shows the accuracy and the validation of the present results. So here is some application of machine learning in computational fluid dynamics, which is used in aerodynamic space optimizations. Machine learning optimize aircraft shapes by predicting performance metric from computational fluid dynamics simulation, enabling faster iterations. It is also used in the improvement of turbulence modeling, leading to more accurate prediction of boundary layer behavior and flow separation. Reduced order model for flight dynamics. Machine learning creates simplified model that recapitulate high dimensional CFD simulation for real-time flight dynamics, aerodynamics, and heat transfer. It enhances computational fluid dynamics prediction of heat flux and shock waves behavior for hypersonic and re-entry vehicles. So these are some applications related to the present work. So at the end, the main key finding of the present work are: with the higher values of the Kazan fluid parameter, fluid velocity and boundary layer thickness decreases. As with the increase of Kazan fluid parameter, the viscous force in the fluid increases. That's why the velocity of the fluid decreases. So drag force for the wall in the case of the Kazan liquid is higher as compared to the non-Newtonian fluid, because the Kazan fluid, the present work in the present work we have studied Kazan fluid. So in the case of Kazan fluid, drag force wall is higher as compared to the Newtonian fluid. Thermal field become higher due to the thermophoresis parameter. For a greater thermophoresis, the fluid concentration become higher. The Laurent force, the present machine learning model demonstrate the strong capability for evaluating the MHD Kazan nanofluid model on the stretching surface. Training data set are used as an input and target value for the multiple case to generate the accurate predictive outcomes. This approach ensures the data-driven validations and reliable prediction of the model behavior. Thank you. If you have any question.
Okay. Any question? Sam, you mentioned about shape optimization, how to use in machine learning with shape optimization.
Sorry, Professor, shape optimization?
Yes.
Yes, Professor.
Yes,
Actually,
you mentioned machine learning, how to optimize.
Yes, Professor. Professor, actually, it is used in the aircraft wings by using when we find the data from the machine learning, then we use this data to find the accurate prediction. For example, if we want to shape the aircraft wings, how it can be shaped accurately by using this data. It bear the pressure of the air. It bear the pressure of the air, and it moves it moves for a long time. That's why we have to do the machine learning when we flew the model in term of aerodynamic space, in term of aerocrafts. We have used machine learning that on the machine learning on the fluid dynamics model to predict the data, to check the performance of the aircraft wings.
Okay.
Yes. Thank you, Professor.
Okay, thank you, Ramzan.
Thank you very much, Professor.
Right. Thank you, Dr. Lamsan. The next is Saki. Please share your screen.
Hello, everyone. Is my screen visible to everyone? Can I start, Professor?
Yes.
Yes, sure.
Good afternoon, everyone. I am Dr. Saki Murtaza, and today I will be presenting my postdoctoral research work entitled Mesh-Free Modeling of a Generalized Dusty Two-Phase Hybrid Nanofluid Flow in a Confined Channel via Radial Basis Function Method. This work has been conducted under the supervision of Professor Dr. Phom Kumam. Before we begin, let me briefly outline the structure of this presentation. I will start with the introduction, providing an overview of the study. This will be followed by the research background and a concise literature review to establish the context and the current state of the knowledge. I will then highlight the research gap that motivated this work, leading to objectives of the study. Next, I will discuss research methodology, including the modeling approach and solution techniques. The core presentation will cover modeling and results, showcasing the key findings. Finally, I will conclude with concluding remarks. It's an overview of the presentation. This study develops a fractal fractional two-phase dusty hybrid nanofluid model to analyze the combined effects of non-nitrate and molybdenum disulfide particle dispersed in grease aimed at enhancing heat transfer and flow performance in confined microchannel lubrication system. Let's look at the research background. In this section, I will present the basic terminologies that are involved in today's presentation. Let's start from the fluid dynamics, the very basic and fundamental term. And it's a study, fluid dynamics is a study of fluid's motion and its behavior. And it has so many applications, but here I will mention a few of them. It has applications and we can study ocean tides, weather patterns, air conditioning systems, and wind turbine. We use so many equations in fluid dynamics, but here the fundamental ones are the Navier-Stokes equations, which we use for the momentum diffusivity. Fourier's law of heat transfer we use to analyze the temperature distribution in the systems, and Fick's law is using for concentration of mass. Flow, motion of a fluid in response to applied forces. And we have two classes of flow. The one is single phase flow and the second one is multi-phase flow. Single phase flow consisting of only one phase, either liquid or a gas with one phase change. While on the other hand, multi-phase flow involves the simultaneous flow of two or more distinct phases that can be liquid, gas, or solid that interact with each others. And we have examples, oil, water, and gas flow in petroleum pipelines, which is an example of three-phase flow. But the special case of multi-phase flow is a two-phase flow, which is our present study. Two-phase flow is a special case of multi-phase flow where two distinct phases, liquid gas, liquid solid, or gas solid moves together in the same system. Examples are sand particles transported by the waters in river and steam water mixture in heat exchangers or boilers. Let us now examine the existing literature on the topic of two-phase dusty hybrid nanofluid flow. In these sections, I will summarize the key development and focus on the most significant contribution that have shaped the current state of research. Foundational studies were conducted between 1960 and 1970. This era marks the early development of two-phase flow research. In 1962, Sefman introduced the first mathematical model for two-phase flow, laying the groundwork for future investigation. Subsequently, in 1965, Mikhail extended this model to analyze particle motion in viscous fluids. These pioneering studies established the basic principle and methodology that have guided subsequent research in this field. During this period, research on two-phase flow and particle-laden system moved from foundational study to more advanced theoretical modeling. In 1971, Cox and Mason analyzed the behavior of suspended particles in fluid flow and developed coupled momentum and energy equations. Later, Pi extended this work in 1977 by presenting mathematical model for two-phase compressible and incompressible flow. This era, from 2000 to 2015, present a transition from purely theoretical model to advanced computational approach. In early 2000s, researchers refined dusty gas theory to include unsteady and heat transfer effects. While in mid-20s, researchers integrated additional physical effects such as magnetohydrodynamics, porous media, and thermal convection, extending the applicability of two-phase flow models to more complex engineering systems. From 2010 to 2015, the focus shifted towards computational modeling, including radiational effect, nanoparticle enhanced fluids. In this slide, I will present the fundamental papers which motivated me to model the present research work. In 2019, Ali et al. Developed a two-phase oscillatory density flow model incorporating viscoelastic behavior, viscous dissipation, and heat transfer effects, providing a strong physical and mathematical foundation for analyzing coupled fluid particles dynamics. In 2021, Khan et al. Examined two-phase density flow influenced by wall shear stress, employed the Pioneer Lighthill perturbation technique for semi-analytical analysis. This research extended the theory toward complex flow boundaries and interaction forces relevant to confound geometries. These two articles form the basis for my present research work and provide me a comprehensive research case. The literature survey reveals that the previous study employed linear partial differential models solved through integral transform techniques or any other analytical techniques. However, a comprehensive fractal fractional formulation of a density hybrid nanofluid with an inclined microchannel has not yet been reported. Therefore, to bridge this gap, the present study numerically investigate an oscillatory, time-dependent, incompressible two-phase density hybrid nanofluid using the radial basis function mesh-free method. These are the objectives. The first one is to develop a fractal fractional model for density two-phase hybrid nanofluid flow in inclined microchannel. To examine the influence of boron nitrate and molybdenum disulfide nanoparticles on velocity and temperature distribution. To apply the mesh-free RBF method for accurate numerical solutions for the governing equations. To study the effect of key dimensionless parameters on flow and heat transfer behavior. To evaluate the enhancement in heat transfer rate achieved by hybrid nanoparticle suspension. The research methodology will be initially start from the mathematical model that will be formulated in terms of dimensional partial differential equations accompanied by appropriate initial and boundary condition. Subsequently, suitable non-dimensional variables will be introduced to render the governing equation dimensionless. And the model is further generalized by incorporating the fractal fractional derivative operator. For the numerical solution, a local radial basis function scheme will be employed. Graphical and computational analysis are then performed to visualize the results. And finally, conclusions are drawn based on the obtained solution. The model investigates the two-phase density hybrid nanofluid flow in an inclined microchannel. The microchannel consists of two inclined parallel plates separated by a distance d. The hybrid nanofluid flow is assumed to be incompressible and one-dimensional along the x-axis. A constant magnetic field of a strength B0 is applied transversely to the fluid flow, while the base fluid is assumed grease, and boron nitrate and molybdenum disulfide are considered as nanoparticles to form homogeneous mixture of density hybrid nanofluid flow. Now let's talk about the governing equations and mathematical modeling. The first equation represents hybrid nanofluid velocity equation, law of momentum and some basic assumptions. The second equation represents dust particle velocity equations. Equation 3 represents hybrid nanofluid temperature distribution equations, while equation 4 represents the dust particle temperature distribution equations. And these are the associated initial and boundary conditions under which we have analyzed our fluid phenomena. In the next step, we will use some dimensionless variables to make our dimensional system dimensionless. After incorporating the dimensionless variables, which are defined in equation 6, we will get a dimensionless hybrid nanofluid velocity equation. Dimensionless dust particle velocity equation will be in this form, while dimensionless hybrid nanofluid temperature equation and dimensionless dust particles temperature equation will be in this form. And these are the dimensionless initial and boundary conditions. Now in the next step, we will generalize our model by incorporating the fractal fractional derivative operator And after incorporating the fractional derivative operator, we will get our system of governing equation in this form. Equation 12, 13, 14, and 15 will be solved numerically by built-in MATLAB software for the graphical solution. Here on the left-hand side, we have an operator that are defined here with exponential kernel. During the dimensionless process, we get some dimensionless physical parameters, and the summarized form of that physical parameters are we have in this chart. For parametric analysis, we will use these parameters and we will draw some graphs. Figure 1 illustrates the comparative analysis of classical fractional and fractal fractional model. And it shows that the operator leads to a reduction in the velocity profile due to enhanced memory effect. And additionally, the inclusion of hybrid nanoparticles and unary nanoparticles improve the flow performance compared to individual nanofluid. Figure 2 represents variation in velocity profile in response to increasing value of thermal Grashof number. And it plays a critical role for determining the fluid behavior influenced by thermal effect. As the value of GR increases, the buoyancy forces become dominant over viscous forces, allowing the fluid to flow smoothly in the system. The parameter GR plays a crucial role in natural convection phenomena such as cooling of electronic devices, heating of vertical plate, automotive industry, and lubrication process. Figure 3 shows the impact of volume fraction on velocity profile. The figure shows a decrease in the velocity profile with increasing value of volume fraction. As the volume fraction increases from 0 to 0.04, which means 4%, the effective viscosity of the fluid increases, making it more viscous. And consequently, this increased viscosity leads to slow down overall motion of the fluid within the microchannel. And we have observed decreased velocity profile. On the other hand, Figure 4 shows the influence of the dust fluid parameters N on the velocity profile of two-phase hybrid nanofluid flow. The figure shows decreasing trend in the velocity profile. In dusty two-phase flow, the dust fluid parameter refers to the mass concentration of the dust particle, and it quantifies the interaction strength between base fluid and dust particles. Therefore, increasing value of N indicates higher concentration of dust particles, which makes it harder for the fluid to flow through microchannel. And this is because higher concentration produce greater drag forces on the fluid. And we observed decreasing profile with increasing value of N. Figure 5 shows variation in particulate phase of velocity profile and against increasing value of dust particle parameter R0. The velocity of the dust particle increases with increasing value of R0. This is because the dust particle follow the fluid velocity. At higher value of R0, the drag between fluid and dust particles strengthens, allowing the particles to move more smoothly through the system. Figure 6 displays the effect of angle of inclinations on velocity profile. The figure shows an enhancement in the velocity profile with increasing angle. As the angle of inclination increases, the gravitational forces component acting on the channel direction provides additional driving forces to the fluid, resulting in the accelerated fluid motion and enhanced velocity profile. Figure 7 illustrates the impact of fluid particle interaction parameter N1 on the thermal profile of the dusty two-phase hybrid nanoparticles in microchannel. The figure shows rising thermal profile against higher value of particle interaction parameter. This parameter characterizes the strength of momentum and energy exchange between the dust particle and the fluid. Increasing value of interaction parameter imply that the dust particle absorb thermal energy and redistribute it more effectively. Figure 8 illustrates the influence of parameter I on the thermal profile. This figure shows enhanced thermal profile with increasing value of the mass concentration parameter. An increasing value of mass concentration parameter implies a greater suspension of dust particle, enabling the fluid to absorb more heat while distributing it more gradually. Therefore, a rise in the thermal profile is observed. Table 1 presents the computed rate of heat transfer and their percentage enhancement. Nusselt number is calculated for the two cases, unary, referring to single nanoparticle, like individual boron nitride and molybdenum disulfide. And the second case, referring to hybrid suspension of nanoparticles. We suspended both the particle at the same time. The result indicates that when volume fraction is 0, the fluid behaves as a regular fluid in all the three cases. The volume fraction increases to 0.01, the fluid starts to exhibit as a nanofluid, enhancing heat transfer, especially molybdenum disulfide plus grease. The heat transfer rate increased by 1.3068%, and for boron nitrate, it increased by 2.483%. For hybrid nanofluid, the combination of boron nitrate and molybdenum disulfide suspension in grease, the heat transfer rate increases 11.110%. This result clearly implies that hybrid nanoparticle leads to superior rate of heat transfer comparing to single nanoparticle dispersion. Concluding remarks. In the figures, it is observed that all integral curves converge to steady state depending on the value of alpha and beta, which represent fractional order and fractal order. The results indicate that the velocity field exhibits an increasing trend with increasing value of the parameter gr and angle of inclination theta, while exhibit decreasing trends with the higher value of parameter volume fraction and concentration of mass particle. When dispersing, individual 4% of boron nitrate nanoparticle enhanced the heat transfer rate by 11.11%, while molybdenum disulfide nanoparticle enhances it by 10.114%. Dispersion of 4% of the hybrid nanocomposite, boron nitrate and molybdenum disulfide increase results in the highest heat transfer enhancement, achieving an improvement of up to 13.518%. Thank you.
Anyone has any question?
Yeah, please, may I ask?
Yeah, you are welcome, Dr. Sunny.
Oh, thank you very much, Dr. Saki, for this wonderful presentation. So I have few questions, though, as you know, I'm not from that field, so my question may sound a bit silly, but yeah, it's just for the sake of curiosity. Okay, so you solve the equation 12 to 14 numerically, was it 12 to 14 or 12 to 15, right? As you said.
Yes.
Can you take me to the equation, please?
Yeah, I'm taking you to there. Okay. These are the four basic equations which we have been solved numerically by using MATLAB built-in code.
Okay, so my concern or my question here is that why do you solve numerically? Do you have like guarantee of the existence of the solution first before you think of solving it numerically? Or how do you like choose the parameters that will guarantee the solution itself before thinking of approaching it numerically?
Okay, your question is finished, Mr. Sani Salisu?
Yeah, about this one, yes. I still
Okay.
have other questions.
Okay, the numerical technique that we use to solve these vector fractional differential equations, the name of that technique is local radial basis function.
Okay.
And there is a vast literature on that numerical technique, which is very handy for those equation and for those geometry in which we don't need a mesh. Like if we look to the time finite difference technique or finite element analysis, so we need to discretize the domain, and we need
Yes.
to point out the nodes, step size, and each and everything. But
Yes.
that technique works only in those geometry which are regular. So we can divide them like regularly. But when it comes to a non-regular geometry, so we cannot use that equation, that numerical techniques. So then we need a technique which do not depend on the mesh and nodes. So local radial basis function technique is a such technique which do not depend on the meshes and nodes. And we do not need to discretize the models and then solve it. That is the first reason that I choose this technique. The second one, you ask about the solution existence. So we already studied these equations are linear equations, and we already solve by analytical technique and by integral transform technique, and we get the answer from these equations. But some of the parameters we did not get from the integral transform technique or any exact analysis. But we are sure about from the solution that these equation has the solutions, and therefore we go for the numerical technique, LRBF, local radial basis function techniques. But the thing is, I didn't mention in my slides because we have a sufficient time, so we ignore all those things and just limited myself to the basic things to present my work. But we can discuss it later with all these things, as you are expert in numerical solutions and techniques. So we can discuss all these things about the stability, convergence, error analysis, and the solution existence of the models.
Okay. So if I got you correctly, you have the theoretical solution there already. Of course,
Yeah,
then you
I
go
have.
into numerical one, but from the theoretical one, you do not have most of the parameters there. You integrated them for the sake of numerical evaluation, right?
Yeah,
Oh,
you are
okay.
right in this case.
Oh,
But we were just sure about the solution from our graphical analysis. If we look to our graphs, so it converts to their steady states part, which implies that the solutions are correct and we can get and they are satisfying the initial and boundary condition as well at the same time. So that's why we move with that parameters.
yeah, you see, the reason why I ask question is that numerical solutions are just for particular selections of the operators. Indeed, you made mention of the existing handy literature with regard to the numerical aspect. Of course, I believe that should be a benchmark that you people consider for the investigation. But then with that, we could, in my view, we cannot guarantee whether it's the solution exists. But since you already have it done, beside the numerical implementation, that would be great. And yeah, I really appreciate the way you explain it. So my other question is so you started with the literature of two-phase dusty fluid, which leads you to the integration of fractal fractional model. So I would want to know, like, what's guide your selections of the fractal fractional model? Like, what's literature? Because I could not relate from your presentation, like what literature links you to the incorporation of the fractal fractional, and to what benefit would that be in difference to the existing two-phase dusty fluid?
Okay, thank you for this question. Okay, so we have two paths for the literature review to explain in this presentation. Literature review that leads us for the dusty gas theory, the dusty phase flow. And the second one, the second part is actually leading us.
Okay. Am I having network issue? I could not hear anything from your end.
I think Dr. Sakib is out. I don't know.
Maybe he has network issue. So I think we can proceed. That's fine. We can talk later when we see. Okay. Laughhead, please, you can proceed, okay? Go to the next, I think.
Okay, thank
Yeah.
you, Dr. Sakib. Next speaker is Dr. Sani Salisu.
Oh,
You can
might
show
not
your
have-
Early morning for you.
Yeah, good morning from here, Professor.
Sorry, I just lost
I-
the connection.
Oh,
I'm very sorry.
oh, welcome back, Doctor.
Yeah, I just lost the connection as I'm here in KMUTT, but I don't know why I lost the connection. Okay, let me share my screen again.
Oh, okay, in brief then, fine.
Okay, is it visible to you, Dr. Sani?
Yes, please.
Okay, so as I mentioned, as I was explaining that we have two parts to explain the literature review. The one part starts from the foundational study of the two-phase dusty flow, and the second one was about the classical calculus, and then leads to fractional and fractal fractional. Okay, so I already mentioned about the literature of the two-phase dusty fluid flow, that from where it starts and how it gives me the motivation to study. And the last paper was actually discussed by Khan et al. It is actually Mr. Daulat Khan, maybe you know. He was our lab members. And the co-author is also Professor Pom Kamim. So I was studying this paper, and this gives me a motivation that I have to extend this theory to include the fractal fractional model, because it was only solved by the classical theory. So then I include the fractal fractional. Why? Because classical theory did not give us a memory effect of the fluid phenomena. And when it comes to the continuum hypothesis theories in fluid dynamics, so we need a fractal calculus, because it has an extra fractal dimensions that clears the continuum hypothesis theory. Because we have two cases in fluid dynamics. When we are studying the fluid mechanics or fluid systems, so we suppose that every property, every intrinsic and extrinsic property of the fluid system is same everywhere in the fluid system. But on the other hand, if we do not suppose that the properties are not same everywhere, so we need a theory that explain all these properties individually. So therefore, I choose fractal calculus in my literature.
Okay, thank you very much for the explanation. That would be all
Welcome.
from my end. Yes.
Thank you.
Good.
Anyone have any question? Okay, thank you, Dr. Sakib.
You are welcome.
Next speaker is Dr. Sani Salisu. If you're ready, you can share your screen.
Okay. What is happening? Okay, thank you very much for having me today. I will start by appreciating the organizers for this particular event, okay? Today I will be discussing about fixed point of certain class of mapping, but basically it's not the discussion is not going to be centered to the fixed point, rather to that particular class of math and how we were able to come up with something from it. Okay, so I will not go into the details of fixed point theory, like how it starts. It's very lengthy literature, started long ago, to the extent that recently people consider the area to be like in its saturated state, though I'm not in such belief. But anyway, we are going to decide by the end of this presentation. So the presentation is going to be on the topic strictly pseudo-constructive mappings in metric spaces. Generally, we do not know anything strictly pseudo-constructive mapping in metric space. What we know is in Hilbert space. But recently we come up with this notion of strictly pseudo-constructive mappings in metric spaces. And of course, there are fixed point approximation in certain nonlinear space, because the definition itself exists in Hilbert space according to the Browder and Petrician. But for this discussion, we are going to see how the definition is in the general setting of metric space, and how you are going to link it with fixed point approximation in even spaces that are not necessarily Hilbert or not necessarily even linear. Okay, and this is joint work with my advisors, of course, Professor Fumkem M, Associate Professor Somphon Sariwangsa, and Professor Vasile Berende. So this, the work is published, but here is just to put you through so that you can see how some things could be obtained just by small adjustment, or let me say by something that may appear to be negligible for some of us, but yet that would lead to a very substantial result. Okay, so you may recall that a fixed point, you have to say fixed point of a map first. And for you to have a map, you need to have two sets. First, domain and codomain, then you can have a map. Then the fixed point of that map is the point from the domain of which is preserved under the map operation. That's to say T phi equals to phi, actually. So this is the condition to warrant you having fixed point. So such point that satisfies this equation is what we call a fixed point. If you're not here, what we only need here is just a map. We do not say anything with regard to the setting. We do not say anything with regard to whether it's been metric or it's been Hilbert or it's been, for example, Banach space and what have you. So what is required here is just to have an operator, and then you can talk of the fixed point. And you may see that here for this operator, we only need domain and codomain, which they are not necessarily the same. Okay, sometimes you may have it D to D. Of course, in that situation we call it a set mapping, but here we just have it from D to another set H, let's say. So this is different. Okay, so this is like the general one. Okay, and you can have it to D to X, any set. Okay, once you have two sets and then you have a map mapping from one set to another, then you can talk of its fixed point, provided that the domain and the codomain of that map intersect in at least one point. That's the condition. So if it intersects in at least one point, we can ask several questions. Among the questions that you could ask, the very fundamental one, starting with whether that map has a fixed point. If it has, then you can also ask, is the fixed point unique or not? Is it just one fixed point, or it has more than one fixed point? You can ask that question as well. And even if you know that the map has a fixed point, or you assume it to have a fixed point, then the question of how do you get that fixed point also come in place. Okay, so the idea here is that you may have a map which does not have a fixed point, and you may have a map that has one fixed point, and you may have a map that has a lot of fixed points. It could be 2, 3, and it could be infinitely many fixed points. So in that case, you have to deal with several scenarios, okay? And then even if you are sure that that map has a fixed point, then the question of how do you get that fixed point arise, okay? So now, you can see in this graphical overview here, if you consider this, of course, this the variating one here is the identity one. So the intersection of it with any of the map here is what becomes the fixed point. So if you look at this one here, it intersects the green only in one place. That is to say this map has only one fixed point, and that is it here. So it has only one fixed point. But if you look at this one here, pink one here, you see here it intersects in 2 points. It tells you that it has two fixed points. But if you look at this one, then it tells you that this map has no fixed point because it doesn't intersect with this. So you can see how it works. And if you look at this x plus sign x, then it tells you that, of course, this map has infinitely many fixed points. So this is just to justify that you can have this even in when you are considering a map from R to R, okay? So this is just for you. So now, the setting of the work that we are presenting is a metric space. So, but you may have to also understand certain class of metric spaces that are very, very fundamental in terms of approximation. So I will start by giving you the details of this. So if you have a metric space, and it turns out that every 2 points in that space is linked by a map, which we call it geodesic path. Of course, this map could have different name, but here we refer it as geodesic path. If it satisfies this property, that is the gamma of the initial point 0 here is U, and that of 1 is W, and then you have the isometry. So generally, this isometry is what gives the overview, okay? So the isometry there is for you to translate the normal real line into a curvy space, into like a space that are dealt with curvature, whether it is sectional curvature that are bounded below, yeah, that would be great. But if it doesn't, provided it is bounded, then you can use this kind of definition to have a lot of things. So of course, the image of such mapping under that set, then it's called geodesic segment, and is also very important. So if it turns out that for every 2 points you have the segment to be unique, then in that case you call that space geodesic space, and uniquely geodesic space if it's unique for every 2 points. But if it is just existent for every 2 points, you just say geodesic space. No need to call it unique, okay? So there are several examples of such spaces. Some of them are concave spaces that are known by most of you there from the lab. But of course, these concave spaces are actually named by this Russian-French mathematician, Michael Gromov. Of course, in 1987, and what suggested this name in cut by him is the work of 3 very, very essential mathematicians. Of course, the Cartan, who is a French mathematician, and that of Alexandrov, who is a Russian mathematician, and that of Tofonov. Of course, this one also is Russian mathematician. So you see from French, this one is from Russia to French. So this French and this one, they are all Russian mathematicians. So them, because the Cartan dealt with differential geometry, Alexandrov dealt with the curvature, and then Tofonov dealt with, of course, the link between the geometry and that of curvature, yes. So that comes, sometimes you may see the name Hadamard space. It's just to refer to a complete cut zero space in most of the work that we have done. So, and it's named after Solomon Hadamard. So this is also a French mathematician. So, and the cut zero, if it is cut zero, then it's compared with the natural triangle, that is the Euclidean one. Then if it turns out for every 3 points and with the segment connecting them, all of them turns out to be slimmer than the actual triangle that we know in the classical or Euclidean setting, then you can call that space to be cut zero. And how do you know whether they are slimmer or not? You can take any 2 points from this triangle and ensure that their corresponding point also in the Euclidean setting is less than or equals to the norm of the difference between the corresponding. So once you have that, then you can guarantee that that space is there. Well, you see, in general, this could be difficult to verify, right? So it's not like an easy job for you to say that, oh, I can check whether a space is cat zero or not just by using this inequality. Okay, then, but there are several characterizations which would help one to identify whether a space is cat zero or not. So some of those, of course, could be stated later on. But here, I don't want to go deep into this geometrical aspect. So, but just to give you overview so that you would have a picture of what we have done in this particular work. So, but the interesting part is that you can ask of motivation. Why is that so? So in that case, I can give you some examples. Look at, this is another triangle. Just by having a radial metric, this is popular metric. You see the triangle is like this. So in that case, this triangle becomes very, very slim, slimmer than that of the classical Euclidean triangle. And you can have a river metric also. The triangle is in this form. This one also turns out to be slimmer also. And you can have, when you change to another metric, you have the triangle like this, which as well is also slimmer. Depends on how you evaluate it, okay? So all these are triangles. So you can see different shape of triangles that forms what we call each one of the space. Once you consider R2 with the distant radial metric, it's a cut zero space. And if you consider it with river metric, it turns out to be cut zero. And you consider it with the metric that gives this triangle, then it's also cut zero. And as well, the metric that gives this triangle is cut zero as well. But remember, for this triangle is in R3, okay? So you can consider that as well in 3 dimension. This is 2 dimension, this is 2 dimension as shown in the graphical overview, but this goes beyond R2 to R3, okay? Just that we can only have a feeling or visualization of R2, R3, and what have you like that. So that's why I just decided to show you some example with regard to that R3. So you can have many examples of such spaces. It turns out that all free Hilbert spaces turns out to satisfy all that geodesic axioms, and as well their cat zero space. Hadamard manifold are there, R3s are there, Hilbert ball are there, all cat kappa spaces are there. So all of them are example of cat zero spaces, and the relationship is centralized here in the sense that once you have a metric space, so you can have geodesic space, but inside geodesic space is this black. This black is very essential because these ones are free Hilbert space. So they connect the cat zero space and that of norm spaces. But the intersection turns out to just be that free Hilbert space. So cat zero space is what we just finished describing. Of course, you can have cat kappa that are much bigger. For K bigger than 0, you have it down there. But the main thing that we are talking about geodesic spaces here, of course, the whole of this, which are all inside metric space. So now, because we are dealing with metric spaces, there are certain things that one need to be careful about, okay? But some of them are very elementary, very, very fundamental. They are just straightforward to see. For example, in Hilbert space, or let me say just pre-Hilbert space, once you have an inner product space, then you can be able to establish this identity. This identity is not known to many of us, of course, but once you look at it, sit down at your leisure time, you can establish that the inner product of this is actually given this way. So if you establish this identity, then it is natural to say that, of course, this identity, I can generalize it to a distance structure. And then in general distance, you are just going to have d square here, you have xw, where the distance is considered to be the norm of x minus w. So all of them can be represented this way. So you can see from this inner product structure, we now have a distance structure here. So this gives a very fast way for one to be able to establish a substantial result in that dimension. So we have this notation, and this notation in some literature, it is termed as quasi-linearization, of course, and it helps a lot in aiding so many things. So let's go back to the main topic, the strictly pseudo-contractive. Okay, so it is known by the work of Browder and Petrician since 1967. Browder and Petrician gives this definition of strictly pseudo-contraction in Hilbert space. What he does is that he said MAF-T satisfies is strictly pseudo-contractive if it satisfies this inequality. So you can see here it has to do with what I mean, subtraction. Subtraction is there. Of course, difference of two MAF identity and that of the T operator is involved. So there are many things. So this one restricted to the setting of what I mean, linear space. And indeed, for his definition, he gave it in the case of Hilbert space. So this is very essential class of mapping because it has significant properties such as this class of map is bigger than class of non-expansive mapping, and yet this class is also Lipschitz continuous. And once you have the Lipschitz continuity, then you can be able to talk about its fixed point in some sense, because the whole idea of fixed point of contractive mapping started with the Lipschitz operators, of course, even before that of Banach contraction mapping principle. So this is Lipschitz continuous, as it is Lipschitz continuous, and it has substantial application when it comes to differential equation. In fact, most of these classes of mappings were obtained through the process of dynamical system or differential equation, as the case may fall in. So, but what is important for you is just to understand that his definition, he gave it this way, okay? So now that he gave it this way, and we want to have this definition in the setting of, general setting of metric space. So what do? We now actually look into this. We see that, of course, for the first time and the second time here, we could change it to metric, no problem. But what will happen to this one? So we now say, what is the identity that we know in Hilbert space? So we remember the basic fundamental identity of Hilbert space. We use it here to often this one. We have this one, but we don't know anything about this one. So how do we replace it? Then we remember that this kind of thing, we could use the notation I first explained to represent the inner product. And as a result, we come up with this definition. So this is the definition we come up. This is the Q, actually WCUW. So this is the class of Lipschitz continuous map that we explain. So we come up with this definition. And as we come up with this definition, so we try to say, okay, then to what difference is our definition with the existing literature? Okay, we look through the literature. There is nobody that has ever attempted defining case strictly pseudo-contractive in general metric space. So this is the only one that falls in the general setting of the metric space. So then, but there are some attempts. For example, in cat0 space, there is this definition that is given in cat0 space. This definition is given in cat0 space. And also another definition, this one also is given in cat0 space. So, but looking at this one also, this is applicable to all metric space because there is no structure of cat0 or geometry of cat0 that is being used, only the distance structure that is utilized here. But here there is overflows which is in existence of only in unique geodesic spaces. So now the question is, since we claim to have this definition in general metric space, and there is another definition which appears to be closer to, also in metric space setting. So what difference is our definition with this kind of definition there? So we look at it carefully, and then we see that if you change the distance back to norm, then this definition here that was given by Aremo et al. In 2018, actually this definition will not reduce to the actual definition of Browder and Petrician, which is the central point of investigation. So, so this definition in ideal sense, it shouldn't be tagged as case strictly pseudo-contractive mapping because it does not correspond even when you reduce the setting to Hilbert space. So you cannot have this exactly. And as a result, we say no, then this is not a case strictly pseudo-contractive, even if it is tagged as case strictly pseudo-contractive in the literature. So also, if you look at this one that is in cat0 space, then this has some little trouble. Okay, what is the trouble there? Because you cannot go beyond unique geodesic spaces because of this all-flaws operation. That is one. Secondly, also, you cannot easily obtain the all-flaws because the all-flaws operation itself is an optimization process that is not generally available. So sometimes you will have to deal with it numerically, sometimes you will have to deal with it in a very intricate way for you to be able to manage it properly. So as a result, this is, even in cat0 space, this is not a good definition to utilize. But our definition only uses the matrix. Once you know the matrix, then you check the inequality, and that gives away whatever it is that you want. Okay? So from that definition, we were able to establish that if you have a matrix space, then in that matrix space, the K-strictly pseudo contraction actually coincides with what is called a rich non-expansive operator. In what sense the coincidence? The coincidence is in the sense that if you have K-strictly pseudo contractions, then that should be alpha a rich non-expansive for what alpha? When alpha is K into 1 minus K as given here. Okay? So this suggested so many things, okay? So because now it is just an enrichment of non-expansive, right? Then in that case, then we went further to see what we could obtain, and we show that even in there, provided the metric space satisfies certain inequality, which is what we call Cauchy-Schwarz inequality, if it satisfies that inequality, then you could easily guarantee that that class of map, K strictly pseudo-contractive, is nothing but a Lifshitz map with what kind of constant? Lifshitz constant to be 1 plus kappa on this 1 minus kappa. So as it is. So you can see this Lifshitz constant is bigger than 1. So this is what we establish. And this is very, very important, okay? But then having it to be related to a rich non-expansive, then it turns out that we can establish in some selected spaces like flat cat0 space, the class of strictly pseudo-contractive mappings is saturated. So beautifully, remember the definition we gave, ensure that it coincides with the definition of Browder and Petrician in Hilbert space. That is one. And it's also covered all the other definitions that we stated, because the definition captured that of the one given in cat0 space and that the other one that is also available, or which I said is not like exactly strictly pseudo. So we show in that paper that indeed that definition cover all those classes of mapping. And yet we were able to see that in a flat cat0 space, the class actually is saturated. When we say saturated, we mean that if you are to use geodesic perturbation mechanism, by geodesic perturbation mechanism is just the same thing with averaging of a map. So if you can use that one, then you cannot essentially get any substantial new fixed point result. So what would you have? Whatever it is that you can claim to have done, then it will still remains within the existing literature of strictly pseudo-contractive. That's saturated, okay? If you try to do otherwise, once you employ Krasnosowski mechanism, then that you will end up falling in the same category of strictly pseudo-contractive mapping. This is beautiful because this flat cat0 space also includes a Hilbert space. So this result translates to Hilbert space, of course, where such kind of theorem is established in the work of Professor Vasile Berende and his co-workers. Okay, so beside that one, we were able to say that this Krasnosowski mechanism of iteration, Krasnosowski-Man iteration, of course, that is popularly known for class of non-expansive mapping, it could also be used to approximate the fixed point of that mapping in cat0 space. So this is it. So once you have this one, we're able to show that its delta converges to a fixed point of T. And then when you are in finite dimensional, of course, you end up having the strong convergence, or when you are in compact setting, then you have the strong convergence. There are several things actually. So this is one of the essential convergence result, but this is with regard to the complete cat zero, because this Krasnostersky-Man iteration is only available in unique geodesic spaces based on the O flux rotation. This is essentially a very important theorem. So, but geometrically, what is this strictly pseudo contraction? So since we were able to establish that this strictly pseudo contraction actually coincide with the concept of a rich non-expansive, then you can be able to estimate it in some sense, and they're in the sense of a rich non-expansive. And how will you do that? If you look at this one, for example, we said a map is non-expansive whenever you have the distance between tx to y is less than or equals to the distance between x and y. And this is, yeah, just to tell you a form of intuitive view of what non-expansive is all about. This is tx, for example. If you have a x and it turns out its tx is here, then you have a y, it turns out its ty is here. So you see that the distance between tx and ty is actually less than that of x and y. And this kind of map is called non-expansive map. But in that case, we are after what we call a rich non-expansive mapping. So since we are after a rich non-expansive mapping, so in the case of a rich non-expansive mapping, it is not tx and ty that matters. What matters is the averaging, the t average. And what is t average is you consider it in this sense that t lambda x is 1 minus lambda x plus lambda ty tx. So this t averaging is what is there, but in the case of cat zero space, or in the case of unique geodesic space, we consider this notation instead to represent this. So what it says is that we don't necessarily need tx or ty to be less than or equals to xy. Rather, we only need to guarantee t lambda x, t lambda y here to be less than or equals to the norm of x and y. And this helps a lot to guarantee that. And what kind of map is there? So sometimes even when tx and ty, the distance between them is bigger than that of x and y, provided the averaging distance shrink to be less than or equals to x and y, then yeah, that is very enough for us. And this is the initial definition that was given by Vasile Berende in 2019, and then later studied in so many articles. So in the general metric structure, it doesn't have to look like that, okay? You could have it this way, where you have the distance, look at it here, d of xy. If you look at this, d of tx ty. If you look at this, d of tx ty is bigger than that of d of xy. But it turns out that d of t lambda x is t lambda y is less than or equals to dxy. So this is to tell you that this is a rich non-expansive, even though it is not non-expansive. So this is just to have like a graphical view of what this is about. So you can have a lot of classes, like example of mappings that are not necessarily non-expansive, but they are this class, and it's very essential in the literature. So the main work with regard to this concept of a strictly pseudo-contractive metric space is published here. For those that are interested in the article, you can scan this QR code and you have the access of it through the journal, okay? And then other articles that are related, we have them here. You can all set them as you so wish. Okay, thank you very much for your attention. Thank you for listening. Any question or observation, please?
Question I have.
Yes,
Sunny, in the
Yes,
second
please.
page, you mentioned about if the fit point is uniqueness. How to
Yes.
be a uniqueness.
Okay.
If
Okay, thank you very much, John. Okay. Okay, yes. So what we said here is that first, once you have a map T here, then you can talk about its fixed point. So that map don't necessarily need to be like a self map. It could be from one set to another set. The only thing that you needed to discuss the notion of fixed point is that the intersection of the domain and codomain is not empty. So, and if it is, then in that case, if the intersection is not empty, then you can talk about fixed point. So some of the math have a fixed point, some of them don't have fixed point, some of them they have unique fixed points, some of them have many fixed points. So in this example here, there are 5 mappings here. Look at 1, 2, 3, 4. Then the other one is the identity one, okay? So we have all of them. So I want to use this to illustrate like how fixed points behave, okay? So if you take the math tx to be equals to 3 minus x, that is when you are considering t from R to R, then you are going to have this math, and this math has only one fixed point. So this is the only one fixed point that is there available. So you can see this has one fixed point only. So, but if you take a math tx, x plus 3, then in that case, this one here, you see that this has no fixed point. There is no fixed point at all. So, and also, if you take a math, and the interesting part is that both 3 minus x and x plus 3, they are all non-expansive. So you can see that both two non-expansive, one of them have no fixed point, the other one has only one fixed point. And then also tx equals to x itself is a non-expansive map, but it has infinitely many fixed points. So you can see just in class of non-expansive, you can say one has fixed point, one don't have fixed point, the other one has many fixed points. But if you take, for example, here, x squared minus 1 as well, if you look at it here, you are going to have this map, and this has 2 fixed points because it intersects in 2 points. So also, if you consider this one you have infinitely many fixed points. So this is x plus sine x, of course, which is a rich non-expansive. Of course, you can easily establish something like that. So this tells you that sometimes you have fixed point, you may not have fixed point. But the interesting part is that once you are dealing with Lipschitz continuous mapping, then in one way or the other, you can be able to say something about the fixed point easily, because the existence of the fixed point itself for the Werner contraction mapping, you can see when the Lipschitz continuous constant there is less than 1, then you can guarantee the existence and the uniqueness of that fixed point. And recently, with this notion of a rich non-expansive or a rich contraction, then even when the Lipschitz continuous is bigger than 1, provided it satisfies that inequality that is given, then in that case, you can also guarantee existence, uniqueness, and as well, even approximation in terms of Krasnodębski iteration. And this is very substantial improvement with regard to the existing literature. So this is what I have. Yeah, thank you so much for the question.
Okay, one more, Sunny. For
Yes,
the
please.
English non-invasive mapping, you define on geodesic spread. They can come back to original one.
Yes.
Definition of the
So
mapping.
yes, here I don't really have the definition of a rich non-expansive mapping per se on this presentation, but the same way that this definition of strictly pseudo-contractive mappings goes back to the original definition of strictly pseudo-contractive, also that of a rich non-expansive mapping is also given in general setting of metric space, and it goes back to the original definition of strictly a rich non-expansive once you go back to Hilbert space. So, and that's the interesting part of it. So the interesting part is that our definitions are available for all metric spaces because we only use distance notion. And also when you reduce it to the setting of Hilbert space, provided you let D to be the norm, the norm defined by the inner product, that's okay. Then you will have it to be the original definitions of both in the sense of strictly pseudo-contractive and as well in the sense of a rich non-expansive mapping.
Okay, that's the idea for extension.
Yes.
You must come back to original one.
Exactly. Yes, must go back to original one because otherwise it's not. So that's why I say that even though they have this definition, because this definition does not go back to the original one, then I believe it's not ideal to call it case strictly pseudo-constructive mapping. But this definition was given in 2018 in an attempt to give like a metric definition. But luckily for our definition, it reduces to the original yes definition.
Okay, thank you, Sunny.
You're welcome. Any more questions, please?
Yes, Sunny.
Go ahead, please. If
Sunny, I want to know kappa in I I don't know what's the meaning of code 0 to code 1 or not.
this one?
Yes.
Okay. Okay, like this is close 0 and often 1, okay? If you see
Open
representation like this, it means often 1, okay? Because you know, if you are dealing with people that write manuscript a lot, so sometimes you represent vector, for example, in terms of u comma w. So you see like this one here, you say u comma w. But here, if you say kappa in 0 comma this in often, then it will you know, look different. So in that case, they prefer to use this kind of often to mean often 1. Okay, that's what it means. So whenever you see notation like this, it means often 1, not close. Okay.
Kappa can be in real number or not.
No. Kappa here, based on the definition, it must not exceed 1. Okay. You can consider kappa to be less than 0 as well, no problem. But kappa must be less than 1 strictly, okay? Because if it is equals to 1, then you are jumping to another class of math, okay? But kappa can be less than 0. Why would it be less than? If it is less than 0, then it's straightforward to see that it's already non-expansive, and from there you reach that that non-expansive is what? Case strictly pseudo. So that's what we have, but cannot exceed.
Only strictly pseudo-contractive.
Yes, only strictly
Okay.
pseudo-contraction.
Thank you, Sunny.
You're welcome. More question, please?
Yes, Sunny.
Oh, Dr. Abakar, welcome on board. Nice to hear from you. Please go ahead.
Go to slide number 5.
Slide number 5. Interesting. Yes, this one.
Okay. These triangles you are mentioning, do they have similar properties with the regular triangles? I know for triangle, from the name tri, we have 3 angles. So can you
Okay.
count? Do we have 3
Okay.
angles? Yeah. Do they have similar properties with the regular triangle?
Okay. Yeah, you
With the
see, they have extended, or let me say, extended version of the regular triangle properties. For example, they, in their own notion, of course, they also have three triangles. But that way, in that triangles, I mean, yeah, they have 3 angles. So in that 3 angles, they are defined in a different way. They are defined in the sense of Alexandrov angle. So if you know Alexandrov angle, so all of them, they have 3 angles. For example, each point here, this point itself defines an angle, and this one defines an angle at each vertex. So these are the 3 points. Look at this one that is more visible. If you look at this here, here, and here, then you can see they have 3 inner angles like that. If you look at this one, it has its own 3 inner angles. But if you look at this one, you may not see it using your eyes, but they have angle which is termed as 90 degree according to the Alexandrov notion of angles. So in that case, you have it to be 90 degree, this one 90 degree, this one 90 degree, and that's how these ones are defined. But it's not like you cannot guarantee from the classical point of view that in this setting, that the sum of the angles of a triangle must be what do you call 180, right? So you cannot guarantee that one in this perspective because they can go beyond that what you have. But this Alexandrov angle is what defines the angles that they are. But the interesting part is that these are here only to show you some sense of flexibility. For example, if you have a triangle in this form, then you begin to ask questions. So how do you connect two points geodesically? If you connect this point to this point, you are going to connect it this way. So if you have a shape like this one, even if it is not convex in the classical sense, it will be convex when you enforce this kind of radial metric. So sometimes you may have a non-convex problem, yet this non-convex problem, you can view it in the sense of geodesically convex just by using this metric instead of using the what do I mean? Yeah, instead of using the classical metric, the usual metric. So, and the interesting part is that both optimization problems and fixed point problem are not given based on the geometry of that space. The geometry are there only to help us estimate or investigate the existence and estimate the approximations of that particular solution. So, and this helps you because it's now the same geometry that you are going to use. If you cannot get it done through the classical or Euclidean metric, then you can use geodesic metric to see that how you can get those solutions. And this is one of the beauty of such spaces. Hello, doctor, are you with me?
Yes, I'm with you. Okay, thank you for your clarification. One
You're
more
welcome.
question.
Yes, please.
What makes a rich non-expansive mappings important? Why should we study them? Do they
Okay,
appear
very good.
in arising in application or in ODE or engineering applications?
Very good, very good, very good. So, like I said earlier, is that here we were able to establish that this rich non-expansive mapping coincide with the class of strictly pseudo-contractive mappings. And if you follow the literature correctly, the aspects, especially where they discuss more of demi-contractive mappings that are Lipschitz continuous, but those demi-contractive mappings that are Lipschitz continuous turns out to be strictly pseudo-contractive mappings, which essentially are those mappings that arose from dynamical system. Right from the investigation, the introduction of them by Kubitschek and Higgs, then you will notice that it was derived from from differential equation. In their attempt to solve differential equation, they come up with that class of mapping, and then from that class of mapping is solved. So the initiation of the notion itself is from the physical phenomena that was modeled to a differential equation, and from differential equation, in an attempt to solve that differential equation, they noticed that this class of mapping should be defined and investigated so that later in life, people, whenever they come across that kind of mapping, then they can easily link them with the existing literature and have their solutions. And in recent time, these Lipschitz continuous mappings, they are very, very essential. So provided you can say some things with regard to the existence and stability of the solution, and which of course fixed point theory is very essential, and that helps you to manage. And here in our result, we establish already that this class of mapping is Lipschitz continuous, and we even give the Lipschitz constant for whoever is interested in doing so. So we have these properties, and these properties make it useful in most of real phenomena. So in solving differential equation, in fact, the very simple examples that you may come across whenever you just have u prime of t equals to minus 5u of t. So this is like natural differential equation that is straightforward, okay? But it turns out that that class of map, it does not yield non-expansive mapping. But if you look at it thoroughly, you investigate using the property of enrich, you will see that that class of differential equation resulted to what we call to a rich non-expansive mapping. And this model is a model of population growth that usually come or one can encounter in very simple model. That is just one of the example that I can give you now.
Okay, thank you very much for your detailed explanation. And it was
You're
nice
welcome.
to you once again.
You're very much welcome. It's my pleasure to be able to respond to you, Doctor. Thank you.
Thank you.
Where are you, Adamu? We miss you.
Oh,
Yes, you need to come to lab, Professor. Please, more questions, please. Lab head, you must ask question.
No.
Why not? Okay, then if you don't
Okay,
want to
thank
ask
you
question,
for nice presentations, Dr. Sunny.
you're
The next
welcome.
speaker is Dr. Nasiru Salihun.
Okay.
One minute, please. Adamu, where are you now? I saw you attend the conference in China.
oh, Prof, I am in China now.
Yeah, you can share some conference if you know. Very interesting. I saw the picture.
Okay, Professor.
Okay, good afternoon, everyone. Can you see my screen? Okay, this talk is going to be on some open problems in conjugate gradient algorithms towards a unified conjugacy condition by me, Nasiru Salihu, under the advisorship of Professor Dr. Pomkam Im. These are the outlines of my presentation. First of all, we are going to look at some optimization framework that leads to the conjugate gradient algorithm. Then this presentation is actually based on some of our recent contribution in these areas, which actually was motivated by some gap we identified in some of the papers we reviewed in the literature. Which most of these papers, some of them are based on conjugacy condition. A conjugacy condition is a condition or is a strategy that's mostly used in designing some conjugate gradient parameters. So based on this, we have so many types of conjugacy condition. So which of these condition is the best? So we are going to look at that and why is that condition is the best. So when we take a minimization problem given by this, which is an unconstrained optimization problem, our target here is to find the minimizer of this function, which mostly this type of problem come up in many applications in engineering and sciences, be it from image restoration, robotics control problem, portfolio, and machine learning and what have you. So many applications. So in order to find the minimizer of the problem, mostly we normally use gradient-based algorithm. If you can get the gradient of the problem you want to minimize, then you can use gradient-based algorithms in order to solve this problem. Why? Is because if you have a large problem, in some instances, you may not use a graphical method or classical calculus in order to find the minimizer of the problem. So most of these methods normally move from one point to another using these iterative schemes, whereby the alpha k here stands for the step size, which is normally computed or obtained using exact or inexact line search. So the eta k here stands for the search direction, meaning that how long we are going to stay in searching for the minimizer or for the optimal of the given problem. So before we look at the different types of or the direction we use in order to get the minimizer, in most of the research, we normally use inexact line search given by either Armijo line search or Wolf line search conditions. We have different versions of Wolf line search condition, but the one given here is the standard Wolf line search condition. Instead of you obtaining alpha k here exactly, we use approximation in order to get it and see that it satisfies some of these two inequalities. The first inequalities is all about talking about the step we take will definitely lead us to the minimizer, meaning that we have a reduced function value when we use this approximation. So what differentiates one method from another method is how we choose the search direction eta k. The first one, which is the oldest among these methods, is the steeped descent, which normally says that you move in the direction of the negative gradients. One of the main drawback of this method is that it's moved in a zigzag pattern, which sometimes causes slowdown in convergence. So based on that, some sorts people now tend to use Newton method. But the main issue with the Newton method is that it requires second derivative information and its storage. Also with together with its inverse. So computing and storing second derivative information for large problems is definitely going to be a problem, because there are some problems that you cannot even get the gradient, talking of the second derivative. So based on that, instead of using exact second derivative information, some approximation were used. This gives rise to quasi-Newton method. So these two, you need to store matrices here, which is also a problem in some instances. So based on this, in order to avoid matrix storage, conjugate gradients were designed. Here, I look at the general form of conjugate gradient search direction, which include 2-term, 3-term, and spectral CD search direction. By spectral, we will discuss it in our future slides. So this is a 3-term. Here, there is no any matrices. The only thing we have is the gradient of the function at point sk plus 1, which is given by gk here. So the beta k here is a CD parameter, while eta k is the direction, that is the previous direction. Pk here is just a scalar, uk also a scalar. Eta k is our spectral parameter. So when eta k is equals to 1, we reduce to the normal 3-term search direction. If pk or uk is 0 and eta k is 0, we have 2-term search direction. So this is how the structure look like. So selecting beta k actually is one of the essential part of research in the area of conjugate gradient method. This research is normally divided into two. Sometimes you work on the search direction itself. In some instances, you work on the beta k. So earlier research in this field normally works on the beta k in general. That is why we have this beta case proposed by so many people in literature. The first beta k was proposed in 1982 by Hastings and Stephens to solve linear system of equation. But when you look at the group of beta case in this group, they have the same numerator. So these groups are categorized by their good numerical performance, but sometimes they may have issue of convergence. That is the one in the second group here. While for the one in the first group, normally they have a good convergence properties, but in terms of numerical, they may not be that good. So based on these two characteristics, so many modification and definition of beta k comes up based on these two characteristics. So if you look at the references, you can see that these are mostly old beta k's. So virtually, if you see any beta k today in literature, it is built upon one of these 6 beta k's. That is why they are important. Now, there is a one of our scholars, that is a great scholars in this area, recently observed in 2011 that despite the improvements in the area of nonlinear conjugate gradient algorithm, still there are some fascinating challenges that remain unsolved in this area. So he come up with a paper whereby he identified 14 open problems that are not answered in the area of nonlinear conjugate gradient algorithm. Some of these are the open problems put on by Nicholas Andre in 2011. So our work today, or some of our contribution recently, especially from 2024 to 2025 recently, are based on some of these open problems. When we look at problem 2, problem 8, problem 9, and problem 13, there are a kind of relationship. We try to a kind of relate them in order to see whether we can come up with the best conjugacy condition in order to design some useful algorithm. Some of our contribution actually, as I said earlier, is based on trying to balance between the numerator, between the beta case with this numerator and the other ones with this numerator. As I said earlier, that most of the research in this field are based on this beta case. So since this area has been in active research for about 60 years up to today, why do we still need to research in this area? There are so many things, but part of what I believe the area is still in existence is that there is no generic algorithm for solving all optimization problems. Apart from that, addressing the problems put on by Andre in 2011 also put many researchers into active research in this area. So our work actually is based on problem 2, which is based on conjugacy condition, problem 8, which is based on spectral, while problem 9, which is based on 3-term, and problem 13 is based on trying to connect between quasi-Newton search direction, Newton direction, and CG direction. How can we make a kind of a connection between them? So before then, the standard conjugacy condition is given by this, which out of our 6 classical CG direction, only beta KHS, when you relate it with the search direction, can fulfill or satisfy the standard conjugacy condition. That is why the beta KHS is very, very important when we look at it in regard to other beta Ks. Because this particular standard conjugacy conditions are normally used when you have exact line search in some instances. In most cases, you require the use of exact line search, which is computationally expensive. So in 2001, Dai and Liu put the kind of relax the condition that you cannot always get 0, but we can use this, which is called a generalized conjugacy condition or weak conjugacy condition. So we can see that this also means that HS method also falls under this, whereby if t is equal to 0, it reduces to, when you relate this with normal search direction, that is the standard 2 times search direction of a CG method, only beta k HS can be recovered when t is equal to 0. So our main contribution actually lies in when t is greater than 0. That is when t is not equal to 0. What will be the behavior of the beta case proposed when we relate them with either 3-term search direction or 2-term search direction? So there are so many research in this area, but most of them are designed based on what we call hybrid technique. Why so? Because as we said earlier, that only beta HS can inherit the standard conjugacy condition. So since other classical beta case cannot inherited the standard conjugacy condition. So we need other ways, other means, other techniques of getting beta Ks inherit or satisfy this condition. So in order to get that, most of these standard beta Ks are being proposed as an hybrid parameter using converse combination techniques. So all these papers we highlighted here follow the same pattern in order to do that. We will see further when we come to some slide whereby these beta Ks were defined. So for the adaptive one, I think there are few papers, except for recent, most of our publication whereby we follow suit, whereby the parameter T here in the definition of the weak standard with conjugacy condition is adaptive, meaning that it's changing as the alteration move on. But in most cases, it's either taken as 0 or taken as 1. It's fixed, I mean. So, but recently there are some papers who try to at least suggest the parameter, but relating it with other search direction. This idea actually was proposed by Jim Q. Liu in 2014, his PhD thesis, whereby it later published as a paper in 2014. He made a very nice contribution towards this because he's one who started this idea of combining a CG direction with a quasi-Newton direction to come up with a CG parameter. Later on, there are some people follow up, which we also take part in this pattern, whereby if you look at the work of Dijovic in 2019, our work of 2020, 2021, then one of 2023, all these were suggested when the parameter T in the weak conjugacy condition is equals to 1. And at the same time, when you have that, the search direction that we use in order to obtain the beta K there normally is either satisfy Newton direction or quasi-Newton direction. So when we observe all this, we now put on a question that is it possible to get a beta K, propose a beta K in such a way that all the 3 instances of the parameter T could be satisfied. That is, for the parameter T equals to 0, for the parameter T maybe equals to 1, and for the parameter T there in the weak conjugacy condition is adaptive. What this is saying is that each of these cases has its own peculiarities when we talk about the convergence of the algorithm. So how can we combine this? At least for now, there is no a unified framework. That is, there is no any work that ever does this in literature. So as I said earlier, that most of the works that took parameter T to be equals to 1, these are some of the recent contributions in that regard. Actually, this work, sorry, this one is for when we take the parameter T equals to 0. This one was introduced by Andre in 2008 when he introduced hybrid CG techniques. What hybrid CG techniques means is that the earlier combining 2 parameters, mini CG parameters, in order to avoid their shortcomings and take advantage of their strength. So he observed that most of the hybrid of projection, meaning that you have maximum between either minimum between 1 or 2 or 3 beta keys. In most cases, you cannot use the beta keys, all the beta keys involved at a time. But when you use converse combination parameter, where the parameter beta key, the hybrid parameter is between 0 and 1, it is possible for you to use all the 2 parameter or 3 parameters involved in this hybridization at the same time. This is the main contribution of Andre in 2008. So this is when T is equal to 0. This is when the search direction is a spectral search direction. This idea is also when T is equal to 0. But here we use standard search direction. That is the classical 2-term CG search direction. While here we use what? We use a spectral CG direction. So when parameter T is equal to 1, we have some of this work, whereby if you see most of the papers that use hybridization techniques in order to get or obtain their CD parameters using these techniques, they also show that the direction that were obtained either satisfy the Newton direction or quasi-Newton direction. For this work of Liu in 2014, satisfy quasi-Newton direction. For the Djofic work, satisfied Newton direction. But for Ibrahim et al., which is one of our pioneer in this lab, his work also use quasi-Newton direction, meaning that it satisfies both the weak weak standard weak conjugacy condition at the same time quasi-Newton direction. So looking at this now, most of this work did not either combine the two. So we look at some of the work in the literature and found that especially the idea proposed by Jian et al. In 2016, whereby he proposed a spectral CD direction, which the such direction satisfy the quasi-Newton direction. But here, he do not consider conjugacy condition in his work. But the main idea there is, in order to guarantee the sufficient descent property of their work, the spectral parameter used there is double bounded, meaning bounded from the below and bounded from the above. When we look at this, you can see that the parameter is bounded below and above. And at the same time, there is a truncation in one of, because in their work, they show that they have two versions of the spectral parameter there. We have theta k plus and theta k minus. So in order to get the sufficient descent property there, they normally truncated some terms in the spectral parameter with the minus for them to get the sufficient descent property. So we see this as a weaknesses. That is one of the major motivation that motivated us in order to go into research into this area, as for the work of Jian in 2016. Later on, we also observed some works by Amini and his co-author, likewise and Wang. So when we observe their 3-term CT direction, we see that they also design their spectral parameter in this format, meaning that they have bounded property, double bounded property. So by so doing, numerically, you mean that some values of theta case may be excluded, so many values. So we try to see that at least we can relax some of these properties a little bit based on the work of Wang in 2023, which he used what? He used only single bounded. So he designed the spectral parameter in this format. So, but in his own work, he do not consider either quasi-Newton or Newton direction. So you can see here too, we have some weaknesses. So based on these weaknesses on these 4 papers, we are able to come up with so many contributions, at least 4 of them. So based on that, we designed some papers. We published some papers, 4 of them, most of which from reputable journals in order to address this issue, whereby our spectral CG directions are designed in such a way that they satisfy the weak Wolf lines, weak conjugacy condition at the same time with either Newton or quasi-Newton direction, making them a little one step ahead of what we have in the literature. And we prove the convergence using normal way of proving the convergence of the algorithms in the CD setting using Zeltenjic theorem. We also show the sufficient descent of these algorithms. So these are the theorems for the sufficient descent, and this is one of the first paper we publish in this regard. For those of us who want to go into the research in this area, in this one, we are able to, because the previous work by Jian et al. 2016 has convexity assumption for the convergence, but here there is we relax such condition. The spectral parameter is also suggested in such a way that it requires double bounded property, but in our own case, we don't need that in this paper. Secondly, we also come up with this paper, which is based on Amini and his co-authors' weaknesses in their paper, and there are 3 times these the directions. We observe that we observe what we observe here, but here we kind of modified the CG parameters because we use PRP here. Here we use HS as in the previous paper published earlier. So the next contribution come up recently, which is based on Flitter and Reeves' CG direction. The last one is published recently, I think April this year. For this last paper, all the 3 papers mentioned earlier, their sufficient descent properties is proved by using line search. But here we are able to show that we can use both line search and we may not require line search in order to prove the sufficient descent property, making it a kind of one step ahead of what we have been doing in the literature. So in this work. So the question of whether we can use combined strategies, that is for the parameter t equals to 0, for the parameter t equals to 1 or any scalar, or any number, that is for the parameter t equals being adaptive is still open, meaning that we are still working on seeing whether we can achieve that. So this is what I have for you. Thank you.
Anyone have any question?
Yeah, I have a question, please.
Yes, please.
Thank you very much, Dr. Nasir, for the wonderful presentation. I really enjoy it, especially the part in which you emphasize on the issue of the optimal value for the conjugacy condition parameter. I just have a question with regard to, it's something that we all know, but I don't know if you have any idea on that. Usually in the conjugate gradient settings, we emphasize on the sufficient descent condition being a requirement for the convergence analysis, and as well as if the sufficient descent condition is satisfied, it is expected that the result, the numerical computation, is going to be efficient. But I observe, I don't know, in my own part, the multi-objective organization settings, even if the sufficient descent condition is being satisfied, that does not guarantee that the numerical computation is going to be efficient. So is there any reason that you can give that possibly I may feel being carried along with based on, maybe based on the classical settings? Does this thing actually happens in the classical settings? The sufficient descent condition is being satisfied, and then you compare your result with the result that the sufficient descent condition is not satisfied, and yours is still worst. Is there a case like that in the classical settings?
Actually, the issue of sufficient descent condition come up as a result of
I think one of you there in the lab should off his mic, please, because there is echoing. It's echoing.
The concept of sufficient descent property and the numerical performance, I think they are two different things. Because when you propose a CG parameter and you test the parameter, it satisfies the sufficient descent property. That does not guarantee that the performance of that algorithm will be good. What that is just saying that if we move in consecutive steps, the step we take will definitely lead us to the minimizer. That is what the theorem is saying. So, being propose a CD parameter that satisfies a sufficient distance condition cannot be a guarantee that the numerical of that algorithm will be good. So that's why even I do not talk much about the numerical, because I know that since we have so many test function in order to test our algorithm A may be good in terms of so test function, while algorithm B is good in other test function. That is even why till today people are still going into research in this area. So if you can have a generic algorithm that can solve all the problem without being robust, so there is no need of doing research. Despite the fact that we have algorithms like Haga and Zank and its type that prove to be sophisticated algorithms when we compare them to some other algorithms, but still you can still see some one or two algorithms that are far better than Haga and Zank and its type when you compare them numerically. So to me, I see it as the best contribution one can have in the area of any research as regard to the conjugate gradient algorithm should be that of theoretical improvement. That's why I keep mute on the area of numerical. Thank you for this observation.
Thank you very much, Dr. Nasser. Because I'm so concerned about this numerical. You will see that you have a very good convergence properties, but the paper may not be able to, go in as the numerical is worse than the one that does not have a good convergence properties. So I'm still having a concern about this. I will see to it. No problem. Thank you very much. I really appreciate your answer.
Thank you, Dr. Z. Thank you.
Hello. Can you hear me?
Yes, we can hear you, Doctor.
Okay, thank you very much, Doctor, for the nice presentation. Yeah. I just want to chip in a little bit with regard to the concept of sufficient descent property in general, not necessarily that relate with conjugate gradient method. So as far algorithms are concerned, the numerical that mostly are given are based on particular cases, not the general investigation. So the investigation is done for a general class of operator or mapping or function in the case of optimization. For example, most of the conjugate gradient method are based on the first order differentiable functions that are bounded below. So most of the conjugate method are based on that. And if you see that kind of method, then you can have algorithms that whose direction is not necessarily sufficient descent. That's to say, you cannot guarantee sufficient decrement of the function's value for each and every iteration. So, but in some iteration, it may decrease faster, while in the other iteration, it may fluctuate. So, and that fluctuations lead to, sometimes it may result to a more faster convergence, because the fluctuation, it depends on how fast it moves. And then if in the process of the fluctuation, it's ended up jumping in the solution, then it will not move further. And that's, in general, could defeat any algorithms that even when the sufficient descent are guaranteed or otherwise. So, but this beta K, my questions with regard to it is that is there any finding in the literature that suggests if you have, for example, two beta Ks and all of them are non-negative, if it turns out that one is bigger or equals to the other one, what is there any theoretical finding with regard to the convergence of the algorithm with regard to these two beta Ks? If the bigger one, will the bigger one gives a more reasonable result, or will the smaller one gives a faster convergence? So all of these are essential things that if it is done in the literature, it will really help, and then we can start to establish more results, because we can say, okay, if we can get a bigger beta case, then we may end up having a better convergence property. But if there is no such finding, then it will be interesting if a live one would consider quantifying the beta case and maybe have like sensitivity analysis to at least say something with regard to behavior of the algorithm in terms of the beta case values, whether they are larger or they are smaller. So this is just my comment, and yeah, thank you. I don't know if you have something to offer here.
Thank you, Doctor. These are some important comments that pose some areas where people can still goes into research, but mostly some assumptions are made, especially when you have hybrid parameters whereby you use those notions of one beta k bigger than the other in order to establish convergence, especially if you look at hybrid parameters in the Riemannian settings and some other settings whereby you have hybrid between PRP and Fletcher Riffs. So some of these techniques are used in order to show the convergence of PRP. But to be truthful, I don't think there is anything from my own side for now that shows that when beta k is bigger than the other, it has so superiority over the other beta k. But only what we normally know is that in the convergence analysis, if the beta k is strictly greater than 0, meaning it is positive, you have a better convergence in terms of the proving of the convergence. So, but numerically, those things are some of the things that we work together, maybe cannot do some of these things. So with time, we believe that in future, if you can have some other people that we can work with, maybe as a group, we can try to see whether we can answer some of these issues in the future. Thank you.
Okay, thank you very much for the response. I really appreciate it. Okay.
Anyone have any question? Okay, thank you very much for my presentation, Dr. Nasilu. Okay. The next speaker, the last speaker is Mr. Jamilu Yahaya in the topic invitation to nonlinear conjugate gradient method for multi-objective optimization. If you're ready, you can share your screen.
Okay, thank you very much. Dr. Nasser, please, can you unshare?
Okay. Thank you.
Okay, thank you very much. Can you see my screen? Hello,
Yes.
can you all see my screen?
Yes.
And can you hear me clearly?
Yes, Mr. J.
Okay, thank you very much. Good afternoon, everyone. All protocol duly observed. I am Jamilu Yahaya. Today, I'm here with you to present an invitation to nonlinear conjugate gradient method for multi-objective optimization problems. I'm also a student from the Fixed Point Lab under the supervision of Prof. Dr. Pumkam M. So the content of my presentation is going to be on these 7 items: the motivation, introduction of the problem, and then method of solution of the problem, as well as the algorithm, convergence analysis, numerical experiment, and concluding remarks. So going with the motivation, I will start by giving the real world problems involving multiple conflicting goals. So in most practical situations, decision affects several objectives that often conflict with each other. For example, in engineering design, sometimes people aim for higher performance of either a particular machine and with a lower cost. But this is usually conflict because usually a high performing machine may not always come with lower cost. As well, in the finance sector, we seek higher return but low risk. This is not actually the truth of the matter. Whenever you expect a high return, then you have to expect a higher risk, which is also conflicting. Also in energy system, we desire for maximum output with minimum emissions, which is not the usual case. So therefore, in order to tackle this problem, multi-objective optimization is essentially good for handling such a trade-offs effectively, rather than focusing on the single optimization problem that my colleague, Dr. Nasser, have just discussed about. So the second motivation I have is with regard to the PhD program. You see, when a PhD student takes multiple coursework while conducting research, there is conflict there. Because the more you try to concentrate on the coursework in order to have a good grade, the more you are leaving your research. And the more you focus on the research, the more you are leaving your coursework. So therefore, you have to combine the two. The most important thing is to find a balance between these two conflicting objectives. That is the coursework and the research work. So since both must be pursued at the same time, then achieving a proper balance between these two objectives becomes essential. Addressing this conflict leads to a more realistic and informed decision-making. So I have been talking about conflicting. So, and at the end, I talk about multi-objective. What is this multi-objective that we're talking about? So from the mathematical perspective, a multi-objective optimization problem is a problem given by this. That is to minimize f of x, where x is from Rn. So it's directly what we are trying to say. We are trying to minimize multiple objective functions. F is from Rn to Rm, which is continuously, usually assumed to be continuously differentiable. And Fi is from Rn to R. So minimizing a vector value function requires a suitable ordering, because since it involves multiple objectives, then definitely we will require a suitable ordering, which is naturally induced by a cone. So in order to solve this, because since we are dealing with a problem that has multiple conflicting problems, then definitely we cannot use the usual optimality condition. We have to use what is called a Pareto optimality. This Pareto optimality, it was introduced by Edward Pareto, I think in 1881, as a concept for solving this kind of problem. So the known method is called the Pareto optimality or Pareto efficient, where instead of using the usual form, we just say if we have a minimizer x star, then f of x star is less than or equals f of x for all x in Rn, then we have a minimizer. But in this case, we have a multiple objective, so therefore we have to introduce this concept. And this concept is introduced as f of x is less than or equals f of x bar for all what? I from 1 to m. And f of x is not equal to f of x bar. So the weak version of this definition is given by this strict less, as you can see in equation 2. So let's look at a particular example, at least 4 examples that deals with this kind of problems. If we reduce this problem, in particular, if we take m to be equal to 2 in problem MOP, we have the following examples. As I mentioned earlier about conflicting, you can see that the first example is non-conflicting. Why is it not conflicting? Because f of x1 and f of x2 are related. If you look at it, the difference is the power. The first f of x1 is x minus 1 to the power of 2, while the second one is to the power of 4. So there is no completion. Why am I saying there's no completion? Because if you solve f of 1, then the solution suffices for the solution of f2. So the common solution here, when we apply the calculus method, then we have x equals to 1, which is the solution for both problems. But if you look at the second example, there is strong conflicting. Why? Because if the minimizer of f1 is actually 1, but the minimizer of f2 is minus 1. So therefore, our target is to find a unified solution. But in this case, we do not have 1. Then definitely there's conflicting. How do we find the conflict between these two? We are going to see it later. The second problem also, or the third problem rather, x squared and x minus 2. You can see that if we solve f1, the minimizer is going to be 0, while f2, the minimizer is going to be 2. And so there is going to be conflicting because we have two solutions, instead of having one solution. While in the last problem, we have x minus 1 as the f1 and x minus 1.5 as x2. So there is conflicting, but a weaker one, because there is a close relationship between 1 and 1.1. So therefore, we have a solution that we may say a common solution at near to x equals to 1.25. So I want to take this particular conflicting example, that is the second example, and discuss about it. Each objective individually is minimized. At what? If you look at the f1, it's minimized when x is equals to 1. So in this case, given f of 1 is equals to 0, then f of 2 is going to be equals to 4 at this junction. And also, f of 2 is minimized when x is equals to minus 1. And at this junction, f of 2 is going to be equals to 0, and f of 1 is going to be equals to 4. So if we attempt to minimize both objectives simultaneously, because that is the target in multi-objective transition problem, to minimize both the problems simultaneously. So it is impossible to make both 0 at the same time. Therefore, Pareto set is what is required. The set of optimal compromise point is given by x in the closed interval -1 and 1. So each point in this interval represents a different trade-off between f1 and f2. So therefore, we're going to see it graphically. You can see clearly that that particular example 3 shows that the minimizer for f1 is what? Is is 1, while the minimizer for f2 is -1. So therefore, graphically, this is what we have. But if you want to find a unified solution, that is, you want to solve the problem simultaneously, this is how we are going to have the solution. So this is how we're going to have the solution. As you can see, the sampling problem is going to be the whole of this line in blue, while the part in which it's shaded red is what we call the Pareto sampling. That is where the possible solution the non-dominated solutions are. What I'm trying to say here is that we have objective 1 and we have objective 2. The target is to find a unified minimum between these two objectives. So look at it. The more you come closer to 2 on the F1 axis, then definitely you are making the other F2 worse. The more you move closer to F2 in the F2 axis, then you are making F1 to become worse. So therefore, a unified point where the solution may be favored is at this black dot center, where both F1 and F2 are favored. So as initially proposed in Theorem 2.2 by Luke in 1981, we have a weak Pareto optimality, which meaning that we have a stationary or Pareto critical point if this condition 3 is satisfied. So in order to establish our solution method, we need the following definition of phi, which is given by 4. So this problem, because we want to talk about conjugate gradient method. And in order to talk about conjugate gradient method, one has to, because conjugate gradient method usually start with the steepest descent direction, as my colleague Dr. Nasser have mentioned earlier in his presentation. So in the vector settings, in order to have a conjugate descent direction, then we must have a problem like this. These are unconstrained optimization problems given by 5. Then the solution, these particular problems, is admit a unique solution actually. And why does this admit a unique solution? Is because this phi is a proper closed convex function. So definitely the solution, or let me say the unique solution of this problem is given by problem 6, which is also given as an argument problem. And the corresponding optimal value for this particular steepest descent direction given by 6 is given by 7. So some of the method of solutions that are being considered in the literature for multi-objective optimization problems is the scalarization approaches. Scalarization approaches, we have different approaches of scalarization. We have the epsilon method. We have the weighted sum method. We have several other methods. So I will focus on this in my discussion a little bit on the weighted method. So what it does here is that it is saying that you should find a W in the interior of Rm and define a function f from Rn to R, which is a scalar function. So if you can write this particular function f of x as a relation, there is a relationship between the W and the multi-objective optimization problems f of x. So you assume that this particular scalar problem is smooth, then the solutions of the minimization of this particular f bar is the same thing as the solution of the multi-objective optimization problems. But one shortcoming about this particular method is the fact that this W is very difficult to find, because at some point, some particular objective functions are being favored. So therefore, other methods are sick in order to solve this multi-objective optimization problems. So in order not to transform this problem into another problem like this one, then several other methods have been proposed. One of them is the steepest descent method, which was proposed in 2000 by Drummond. And in 2005, it was extended as a multi-criteria problem. In 2005, it was introduced to vector optimization by Drummond again and Saveto. So other methods like the Newton's method, quasi-Newton methods are also proposed, like in this Ansari and Panda, Chuan, Taiduan in 2013. So our focus in this talk is actually on conjugate gradient method. Thank God my friend and colleague have already discussed about conjugate gradient method, so I will not take long time discussing about it. Just like in the classical settings, the conjugate gradient method recursively generates a sequence of iterate as given in 9, where alpha k is assumed to be greater than 0, which is called the step size or step length. And we're going to discuss about what is required on this particular step size. And dk is the search direction defined as given in 10, while the beta k in this search direction parameter determines the type of CG method we're dealing with. So as I said, I'm going to discuss about this alpha in particular, which is the step size. So this step size usually is determined by a line search, and we have different line search. My colleague have already mentioned them. We have the Armijo line search. We have the Wolf standard or weak Wolf line search, and we have the strong Wolf line search, and we have other like non-monotone line search. So in this case, the common line search we use in this study are the Wolf line search. So the standard Wolf line search is a weak version of the strong Wolf line search, which is given by 11, while the strong Wolf conditions is also given by 12. So one very important requirement that we require in the convergence analysis of many conjugate gradient method is the descent direction, which I discussed after the presentation of my colleague, the descent direction. This descent direction is actually an important requirement in order to be sure that your objective functions are reducing towards the minimizer. So generally, we may require this descent direction, but a more stringent requirement is also needed, which we are going to discuss later. So otherwise, this particular descent direction defined by less than zero, f of x, p of x, comma d, strictly less than zero. The converse of it is actually what you call the Pareto critical point, which is given by this p of x, comma d greater than or equal to 0 for all d. So a more stringent condition that may be required in the convergence analysis of conjugate gradient method is sufficient descent condition. The sufficient descent conditions, as I said earlier during my question, is a very important property needed in the convergence analysis. However, most of the conjugate gradient method established in the classical settings that are being extended to the multi-objective optimization settings or vector optimization settings lost this important property. And it is still an open problem, or we still have many open problems with regard to this. Why are this particular method losing this important property while in the classical settings they satisfied these particular properties? So as I said from my previous slide, that this beta k determines the type of CG method we deal with. So you can see we have different type of beta k parameter. The ones extended, the first set extended in the classical to the multi-objective optimization settings by Pires and Prudenti in 2018 are the FR, CD, DY, and PRP. I want you to look at this beta k parameters. As you can see, these beta k parameters are related somehow. If you look at the numerator of FR, CD, and DY have the same numerator, while the denominator of FR and PRP are the same thing. The denominator, hello?
Can
you hear me? Hello, can you hear me?
We can hear you.
Okay. The denominator of dy and hs are the same thing, while the denominator of CD and ls are the same thing. So it is known in the classical settings that this method, like CD, dy, and FR, are usually called descent methods because they satisfy the sufficient descent conditions under certain conditions. While the PRP, HS, and LS hardly satisfy this particular property in the classical settings. But after the work of Gilbert and Nessedal in 1992, it was discovered that the PRP can satisfy the sufficient descent condition as well as the convergence and achieve convergence under the Wolf line search if it is being restricted to a non-negative parameter. So despite this condition, when these methods were extended to the multi-objective settings, the FR, PRP, HS, and LS lost this important property. And it's still an open problem. Why are these particular problems losing this important property? While the CD and DY actually achieve this property in these settings. Another perspective is that, as you can see, this dy, it is defined in this form. Then recently there were some authors who happened to define dy in a different perspective. As at the same time, both this dy and the other one that is being extended in different form can reduce to the classical ones when m is equals to 1. This also goes to a problem of PRP. PRP can also be defined in a different way, different from this pattern, which we are working on right now. Likewise, HS and LS. So we don't know if they are being defined, since this method can be defined in 2 or more different ways, then we will later on discover why are these maybe one of the definition, maybe since this one could not be able to achieve the sufficient distance condition, then maybe the other form of definition could achieve. As well, the Hajar and Zhang also define in two different forms, and both of them can also reduce to the classical settings. That is one interesting thing about the multi-objective optimization settings. So I talk about the descent property and how it is being lost. So some of the ways to recover this descent property, since it becomes necessary, then we have to consider at least the following: modifying the search direction. Modifying the search direction, this is what we did in two of our papers, and we're able to achieve that. Then redefining or adjusting the parameter. This is also, we did this in some of our papers. You can see them in the literature. Then employing an alternative line search technique. Recently, I saw a paper that established the convergence of PRP using non-monoton line search. As well, there was a paper established in 2022, I think, by Goncaps, where they established another form of solution of LS using an Armijo line search. Also, enforcing a sufficient descent condition explicitly. So this is what they have been doing when they extended the problem. Like the case of first Hajar and Zhang that was extended, the authors enforced the sufficient descent condition in the algorithms. Also, restarting the algorithms is another form. Restarting the algorithms, because most of our problems are under non-regular restart. So we can also restart the algorithm whenever the sufficient descent condition cannot be satisfied, then we restart the algorithm. This is also a good idea. Then another one that I did not write is the one that I mentioned earlier with regard to rewriting some of these parameters in different ways. So the search direction, which I have talked about, is being defined in this form, in this form. Also, what's the general framework of the algorithms of conjugate gradient method? You see, what we are trying to do is to find critical points that are being generated by this particular algorithm of multi-objective optimization problems. The steps are usually the same as the steps in the classical settings. We choose initial values with regard to the X in the domain, as well as the parameters involved in the line search strategy, which are the rho and the sigma, and then we set the initial point. Then in step 2, we compute the steepest descent direction, as well as the optimal value using the definitions from equation 6 and 7. So if the optimal value at this point is equal to 0, then we terminate the algorithm. Otherwise, we find the step size either satisfying the warp line search or strong warp line search. Then the next step, we compute the search direction using this definition and using a suitable beta k parameter. Then in the next step, we update and return to step 2 until we have a solution. Usually this algorithm in these settings, it terminates or it reaches a maximum iteration at 5,000 iterations. And we have a solution which is being reported when V of X is less than a particular negative number. So the steps taken in order to show the convergence in CG algorithms is usually we assume regularity conditions, which is the objective function is continuously differentiable. The Jacobian is Lipschitz continuous, and the level set generated by the iterate is bounded. We establish the line search conditions, which usually the step size satisfies the warp or strong warp conditions, ensuring a sufficient decrease, and curvature properties. And then prove the sufficient descent condition, which I have mentioned. Then show boundedness of the iterate using the descent property. Usually using the first condition that I mentioned, which is the Jacobian and what have you, we could be able to establish the boundedness of this SK, which is the sequence, within the label set. Establish the function merit, which is or function decrease, which demonstrates that the objective function decreases monotonically, showing progress at each iteration. then show vanishing gradient using the solubility result, which conclude that lim inf is equal to this, implying that at least a subsequence of iterate approaches stationary point. So in numerical, what we usually do, we evaluated the result after putting some certain consideration. First, this particular problems or conjugate gradient method for the multi-objective optimization problems have been evaluated or have been coded in Fortran programming first, and then later on they were coded in move to MATLAB programming. So what we usually do, we evaluate based on the number of iterations, function evaluations, gradient evaluation, and CPU time. So one other important thing, since we do not transform and find the Pareto front effect explicitly, then we do one thing. We use the purity metric. And what does purity metric do? Usually, purity metrics used to effectively compare the performance of algorithm in approximating the Pareto frontiers, since we could not be able to write the Pareto front explicitly. So the purity metric evaluates how accurately an algorithm identifies point on the true Pareto frontier. And this can be seen from reference 10 and 11. And the same thing, the spread matrix. The spread matrix are in two forms. We have the delta matrix and we have the gamma matrix. But what they do is that they measure the ability of an algorithm to obtain well-distributed point along the Pareto frontier. So in conclusion, this study presents an extension of conjugate gradient method to multi-object optimization problems. The presentation talks about key challenges associated with extending search directions and the descent directions under warp line search conditions. It talks about assumptions, global convergence of the CG method using the warp line search without requiring restart or assuming convexity on the objective functions. Then various performance metrics are discussed, highlighting the importance in evaluating numerical result, and other open problems and potential research directions are identified for further investigation. Thank you very much for the time given to me to present this invitation.
Hello, Dr. J. Can you hear me?
Yeah, I can hear you.
I have a question or maybe
Okay.
observation. When we look
Okay.
at the classical definition of the beta case, that is the traditional beta case, we have that FR, DY, and CD have the same numerator.
Yes.
I'm talking about the classical definition. So when you come to the other set, we have beta KHS, beta KPRP, and beta KLS. So
Yes.
my question or concern here is on equation 14, because in classical setting, what we have is that beta KCD and beta KLS have some common features. First of all,
Yes.
they have the same denominator and they all have
Yes.
negative in their definition. But here it's like maybe from the tools, some of the tools you use in vector optimization, that makes the definition a little bit different from what we have in classical setting.
Yes,
So
actually,
in addition to that, maybe you can respond to the two questions together. It's
Okay,
like
okay.
I heard you saying that beta KFR, is it, and CD are yet to be, there is no established work that shows their sufficient distance in the vector setting.
No.
Maybe if you can use non-monotone line search, maybe we can come up with something that will help us in showing the convergence and sufficient descent of the beta KFR.
Okay. Thank you very much. Okay, Doctor, as you see, that is why I say invitation. You know, when you are invited to an event, there must be some statement that will romance your mind. You know, so maybe there is DJ, maybe there is this, so that you can come and see it. I deliberately refuse to write the lemma that shows this P of SK in this CD definition, P of SK, comma U of SK. This particular term is negative. okay, is negative in this settings. So that is why I do not want to write it with negative in the numerator. And also at the same time, the term at the denominator of CD is also negative. So therefore, if the upper denominator and denominator are both negative, then the whole thing is what? Positive. Okay?
Okay.
Then with regard to F at the same thing, the numerator and the denominator are both negatives. So therefore, that is why there is no need to write the negativity at the distance. It is a kind of formal way of defining this in this sentence. So it is when you delve into the settings that you'll be able to understand this one, because many people used to get confused with this kind of transformation. As I know in the Riemannian manifold, usually if this one have negative at the denominator in the classical settings, then definitely at the Riemannian it also have negative, right?
Exactly.
Yeah, so it's quite different from from what we have here. And with regard to the issue of this thing, is FR. FR is still an open problem. FR could not be able to achieve sufficient distance condition up to now. Up to now. I think the only paper that modified FR and achieved sufficient distance condition, it was my paper in result in control and optimization. I and Professor Pung. It was the only paper that actually established a modified FR that satisfies sufficient distance condition. But up to now, FR itself could not be able to satisfy sufficient distance condition. While PRP have been established to satisfy sufficient distance condition, while at the same time, LS also using Arminian line search, while PRP was established using non-monotone line search. So what remains is HS, I think HS itself and FR. Okay? As well as the dilute. And one thing I also find very interesting in your talk is the issue of the optimal value for that particular parameter in dilute conjugacy condition. It is also still an open problem in multi-objective optimization settings. And I have been thinking of going into that as soon as possible, especially with regard to the issue of eigenvalue convergence analysis of Babai Kafaki.
Thank you, Dr.
You're welcome. Any other question?
Where are you now, Jamilu?
Professor, good afternoon. I'm in Nigeria.
Oh, yes. Here's the follow-up we give for you apply the postdoc.
Okay, Professor.
Mm-hmm.
Okay, Professor. I sent her email, but she is yet to reply.
Uh-huh. Yeah, I saw your document.
Okay.
Okay, thank you very much, Samiru. Hope to see
Thank you
you
very much,
here
Professor.
again.
Okay, very soon, Professor. Yes, thank you very much.
Okay.
Okay, thank you very much, Mr. Jamilu. Everyone, can you turn on your camera for take a group photo?
Okay, let me stop sharing.
What next?
The Charzuka.
3, 2
Oh,
โอเคนะ พร้อมยัง 3 2 1 อีกทีนะคะ 3 2 1 โอเค
okay. Nice to meet you all once again.
One more จากไหน
Everybody here. 1, 2, 3. Okay.
งงหมดทายหมด
Hi,
อาจารย์
how are you? Where is PE? PE? Hello,
Hello,
how are you?
I'm fine.
Good.
Thank you. And you? When you come
I
back?
will join you soon. We'll go to gym together, okay?
Okay.
Okay.
I miss you นะ
Sure?
my boyfriend
No, your friend?
my husband
Your husband is in China.
no